Hi everybody, welcome to your first organic chemistry lesson. I hope you guys are as excited as I am to be delving into the magical world of OChem. Alright, so we're going to get started in Chapter 1, and Chapter 1 is going to contain mostly review information, although there might be a couple of concepts that are new to you. I'm not going to go over everything in Chapter 1. I'm assuming you guys know what a proton, a neutron, and an electron are at this time. But if you need any background refresher on stuff that I kind of gloss over or don't go into, be sure to read Chapter 1 on your own so you can get that background. Really, where I'm going to dive in is with Lewis structures. And you guys did Lewis structures last year. Of course, that's where you draw the little structural models using the atoms and the electron dots and the bonds. Okay? So what I want to do is I want to review that and also give you some guidelines and a couple of little shortcuts that can sort of help you be able to correctly predict a Lewis structure. This is going to be immensely important for what we do basically for the rest of the year. You're going to have to know how to draw correct Lewis structures in order to get a good idea of where electrons are going to be. Remember, got to make the electrons happy, right? So let's make the electrons happy. Alright, so let's just review a couple of things first here regarding Lewis structures. Alright. So first off, here's the rules. Alright. Number one, the electrons that we're going to map out are only going to be the valence electrons. Alright. And if you remember, valence electrons, by the way, E with a negative sign is my abbreviation for electrons. If you remember, valence electrons are the ones that are present in the outermost energy level. All right. With the atoms that we're going to be dealing with, we're going to be dealing with carbon, nitrogen, oxygen, hydrogen, and the halogens. Those are the important ones to organic chemists. With the exception of hydrogen, all the outer shells will contain up to 8 electrons. That's referred to as an octet, right? Hydrogen, of course, can only handle 2 electrons in its outer shell because it's just got an s orbital, and the s orbital can only hold 2, right? You can figure out how many valence electrons an atom has very, very easily, right? All you got to do is look at the periodic table and see which column it's in. At least the ones that we care about. All right, so, if you look for carbon, you see carbon is in column 4. That means it's got 4 valence electrons. You see, a halogen like bromine is in column 7. It's going to have 7 valence electrons, right? So that's a nice little shortcut to help you keep track of the valence electrons. All right, and whenever you draw these Lewis structures, you want to follow the octet rule, which I previously mentioned. You want to follow the octet rule for carbon, nitrogen, oxygen, and whenever I draw an X, X is just shorthand for any halogen, so chlorine, bromine, iodine, or fluorine. And when we say follow the octet rule, all right, the octet rule states that the outer energy level of these atoms is going to contain 8 electrons. So if you're drawing your Lewis structures, you want to draw them in a manner that each one of these types of atoms ends up with 8 electrons. All right? You never want to go over. You can't have an expanded octet with these guys. There's simply no room for any more than 8. So if you end up with like 10, that's a really good sign that you may have messed up along the way somewhere. There is one exception. There is one occasion on these where you can have an incomplete octet, where you might have less than 8. That is one particular example, and I'll show it to you as we get to it. All right, and of course, as I mentioned, H is going to get 2 electrons. Okay. There's different ways in which these atoms can sort of have a hold on electrons. They can either the electrons can either be part of a bond between 2 atoms. In other words, they can be shared between 2 atoms, or you can also have unshared electron pairs. A particular atom might have a pair of electrons all to itself and not have to share it with anybody, right? And so, you can have different combinations of these shared and unshared electron pairs to get you to, the 8 electrons in your octet. All right. However, there is a guideline that you can go by that basically outlines, for lack of a better phrasing, the preferences of the atoms. All right. At neutrality. And let me draw a little table real quick. That'll kind of help you out with that. That's all. This is also in your book, by the way, but I wanted to go ahead and sketch it out for you guys as well. All right. And this is at neutrality. All right. So that means that this is the case. This is the preferred state whenever each one of these atoms has a charge of 0. All right. So I'm going to create 2 little subcolumns here, bonds and unshared electron pairs. All right. So we'll start with carbon. Carbon, in its neutral state, likes to have 4 bonds and 0 unshared electron pairs. Nitrogen likes to have 3 bonds and 1 unshared pair. Oxygen likes to have 2 of each. Halogens, they don't make very many bonds. They only make 1 bond and have 3 unshared pairs. And then, of course, we have hydrogen, which is sort of an exception. It likes to make 1 bond, and it can't hold any more than 2, so it's not going to have any unshared pairs in its neutral state. I don't like to use the M word very much in here, and by the M word I mean memorize, but this is something that you should memorize. This will make your life a lot easier if you can remember these guidelines, and that's going to make it a lot easier for you to just look at a given formula and be able to draw its Lewis structure if you can remember these guidelines. All right, so I would heavily encourage you to go through and remember these. All right. So we got that in mind. All right, and in a second here, we're going to do some practice Lewis structures, and we're going to do a lot of practice here because, like I said, this is of the utmost importance. All right, what I'm going to do now, before I get into specific examples, I'm going to give you basically sort of the procedure or the process for doing this. All right. Number 1, map out your atoms. All right, so if you're given a molecular formula, like CH4 or something like that, you need to go ahead and put an arrangement of atoms down on the paper that you can go by. All right, and it'll help you, I think, in mapping out these atoms if you keep in mind the table that I just put on the screen. All right, some of this can be trial and error. You might find out after mapping out some atoms and then going through the process that, hey, this violates the octet rule, right? Well, in that case, you might have to map out a different sequence of atoms. All right. Number 2, what you want to do is come up with a total number of valence electrons that you're going to have, right? And this basically is the total amount of valence electrons for each atom. You add them up, and that gives you the total that you need for your particular formula. So, for example, let's say we had CH4, right? That's methane. So you have 1 carbon atom in this formula, and if you look on the periodic table, carbon's got 4 electrons in the valence shell, so that means it's got 4 valence electrons. All right, you have 4 hydrogens, and each one of those hydrogens has 1 valence electron. And that means you have 4 total valence electrons from hydrogen. You add those up, and voila, you've got 8 electrons. Okay, so in this case, in your basically in your map of atoms, you're trying to link those together and arrange 8 individual electrons. All right, there are cases where you might have something a little bit more complex. Sometimes you're going to be tasked with drawing the Lewis structure of a formula that's got a charge on it. Okay, so we have to sort of make a tweak, a little adjustment to the total number of electrons you're dealing with if you're using something with a charge. Whoops. All right, so you're going to add 1 to the total for each negative charge, right? So if your formula had a charge of -1, you would add 1 electron to the total. If your formula had a -2 charge, you would add 2 electrons. Conversely, you would want to subtract 1 for each positive charge, excuse me. All right. So for example, if we had the formula CH3 minus, right? Our carbon, total contribution from carbon would be 4 valence electrons. Our total contribution from hydrogen would be 3, since we have 3 H's, each one of them has 1 valence electrons. 1 valence electron, that gives you 3. And then you have a negative charge. So you would have to add 1 to that, and that would give you a total, oops, come on, there we go, of 8. Okay? Now, we're going to start off looking at neutral structures, but we will get into charged ones in a little while. All right, once you get to this point, you're going to arrange your electrons. All right, and you're going to arrange them according to the rules. You're going to try to make each one of them correctly follow the octet rule, and you're going to try to give them what they want as far as preferred states at neutrality. Now, that being said, there are certain cases where you might have an overall charge on a molecule. That means you've got to have individual charges. So in some cases, you're going to have to assign something called a formal charge. A formal charge is simply the charge on an individual atom within a Lewis structure. All right. If everything's, if there's no charges at all, then we would say the formal charge on an atom is going to be 0, right? But there are cases where you will have, a formal charge to take into account. Let me just show you an example of the one I just did, CH3 minus, right? If I were to go through and draw the structure for CH3 minus, we said that we had 8 valence electrons. All right. In this case, 2, 4, 6, 8. Carbon, in this case, is actually going to have a formal charge of -1. So overall, CH3 has a negative charge. Specifically, that negative charge is going to be on the carbon atom. All right. I'm going to, once we get to the charged species, I will talk about this in a little bit more in detail. But that's just what I simply mean by formal charge. All right. By this time, normally in a class, I would have popped up with any questions several times. I probably would have quizzed you guys on this, but hey, not able to do that. But feel free to go through this, by the way, and select any questions that you can think of, and feel free to send them to me. I'm happy to do whatever I can to help you answer your questions. All right, so all that being said, let's go ahead and start drawing some Lewis structures. All right. Let's start off with this guy. We're going to start off with CH3CO. Okay. All right. So what I'm going to do is I'm going to try to map out these atoms a little bit here. Now there's a couple of different ways I could go. I could go, something like this, making carbon a central atom, and then surrounding it. Oops. Come on. There we go. With other atoms, right? Or maybe I could choose to make chlorine a central atom. All right. Now, I can tell you, obviously, only one of these is correct. Do you see anything wrong with one of these? Give you a couple of seconds here to think about it. What could be wrong with one of these? Well, again, look at your preferred states at neutrality. All right? If you look at the second one right here, you're going to end up in a state where chlorine has to make a bunch of bonds, like 4 bonds. Chlorine hates making bonds. It only likes to make one. Right? You'd also end up in a situation where carbon would only have 1 bond. That is such a deviation from the norm, it's not going to be possible. Right? Whereas if you look at the top one, you have a centralized carbon. It looks like it's in good position to make 4 bonds. Each of the hydrogens looks like it'll probably make 1 bond each. And then chlorine could conceivably only have 1 bond. So this is a good place to start. All right? Let's count up our valence electrons. So for carbon, we have 1 carbon and 4 valence electrons from that. Chlorine, we have 1 chlorine. It's in group 7, so you're going to have 7 valence electrons from chlorine. And we got 3 H's. Each one of them has 1 valence electron. That's going to be 3. All right. So overall, we got to map out 14 different electrons. All right. So let's go ahead and try to do that. All right. Well, we know H likes to make only 1 bond, so let's try this. Let's just draw a single bond for each one of those. All right. We can go ahead and draw a single bond there. So in this case, the H's and the carbons would be all set. They're completely full of electrons. There's not room to draw any more. However, if I count these, we got 2, 4, 6, 8 electrons that are already placed. We need to place 6 more. All right. Luckily, we have plenty of room in the chlorine. It's only got 2 at this point, so we can add, there we go. We can add 3 unshared electron pairs. And if we look at our chart of preferences at neutrality, this fits really, really well with what chlorine, as a halogen would like to do. So this one is good. Okay. And I realize, but I want to emphasize again, I realize you guys have done this before, so I don't want to get too bogged down in it. I do want to do lots of practice to make sure that you got it, although I might not painstakingly write out each little step for future examples, just to give you a heads up. All right, let's try another one. All right, let's try this one. Let's try CH3, CH5N. Okay? All right, so I have 1 carbon, 5 hydrogens, and a nitrogen. All right? If I count up the number of valence electrons, I'm not going to go ahead and map out every little thing here. I'm going to do some of this in my head. I think you guys can probably do this in your head. Total contribution from carbon, we have 1 carbon with 4 valence electrons, so we're going to get 4 electrons from carbon. We have 5 H's, each one of them with 1 valence electron, so we're going to get a total contribution of 5. And nitrogen, we have 1 nitrogen. It's in group 5, so it's going to give us 5 electrons. So overall, again, we have 14 valence electrons that we're going to spread out. All right? And again, what you would want to do is take your CH5N and kind of map out different ways that, you could possibly lay out the atoms. I'm going to find that this one is going to work well. Oftentimes, it's not always the case, but oftentimes carbon is going to end up as a centralized atom because it likes to make so many bonds. All right? So if I draw this, right, the carbon has 8 electrons. These 3 H's have 2. That's great. We're still missing 6 electrons, and we're still missing 2 hydrogens, right? This nitrogen can hold those 2 hydrogens, boom, and it's got its 3 bonds, which it likes. We still need to place a pair of electrons. Oops. And we'll see that the nitrogen, come on. There, that's good. The nitrogen can hold on to them. We have 2, 4, 6, 8, 10, 12, 14. We double check this. This is the great thing about sort of having these, that chart memorized, is that you can sort of go back and double check this at the end to see if you've done it right or not. And we'd see this one tends to make everybody happy. So this is a correct structure. All right, let's try C2H5Br. All right, so for carbon, we're going to have 2 of them. Each one of them has 4 valence electrons, so we're going to have 8 overall. We have 5 hydrogens, each one of them with one valence electron, so that's going to give us an overall contribution of 5. We have 1 bromine. Bromine is in group 7. It's going to give us 7 valence electrons. So that means we're trying to place 20 of them. All right. And again, there's different ways you can map this out. If you do it this way, you'll see that doing it this way allows us to draw single bonds between each of the atoms. Again, the carbons are happy, 4 bonds, no unshared pairs. The H's are happy. We still have to place 6 electrons. Bromine's only got 1 bond, so it can hold them. And as we know, the halogens like to make 1 bond and have 3 unshared pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. Okay, let's try another one. CH4O. All right, carbon, 1 carbon is going to give us 4 electrons. 4 H's are going to give us 1 electron each, again, so that's 4. Oxygen's in group 6, so it's going, since we have 1 of them, we're going to get 6 valence electrons. So we have 14. Now you could try this. You could try mapping it out like this, right? We got 4 H's. Well, carbon can make 4 bonds, right? So, why not start off like this? Well, you got a big problem. We got to put that O somewhere, right? So, the only thing you could do is do that, and that's a big no-no because H doesn't have enough room for all those electrons. So, if that was the case, we'd go back to the drawing board, and we'd try something else. Now, if you do this, you attach the oxygen directly to the carbon. Carbon's still happy. We have 1 more H. We could put it on the oxygen. All right, oxygen does like to make 2 bonds, right? We still need to place 4 electrons, but we do have room for them on the oxygen. And so, boom, there we go. Alrighty. Let's try this one. CH2, CH2. All right, well, let's see. We have 2 carbons, so that means we're going to have 8 electrons. We have 4 H's, so that means we're going to have 4 valence electrons. That means we're going to have 12 overall. All right, so let's see. We got 2 carbons. Those carbons could be linked together. and each one of those carbons could hold 2 of them. And wait a minute. This one's a little bit different. If you do this, you see we've used up our supply of atoms, right? We don't have any more to place. We got C2 and H4. All right, the H's are happy, right? But the carbons are not, right? If you look at each carbon has an incomplete octet. Each one of them only has 6 instead of 8. You'll also notice that we haven't placed 12 electrons, right? We've only placed 10. Count the bonds, 2, 4, 6, 8, 10. So, what do we do here? Well, we haven't seen any cases yet where we have multiple bonds, right? So this would be a case where actually we can place that extra pair of electrons in the middle, right? That kills 2 birds with 1 stone. Number one, it allows us to place the correct number of electrons, 12, and also this allows each one of the carbons to have a complete octet of 8, right? So this would be the overall Lewis structure. So you will have Lewis structures that can have multiple bonds as well. Let's try another one. Let's try, whoops, H2CO. All right. Carbon is going to have 4 electrons, 2 hydrogens will give you collectively 2 valence electrons, and 1 oxygen will give you 6. So that's going to give us 12 in all to place. Okay? Well, again, a good place to start is to make carbon sort of a central atom. All right? And you could try surrounding it with the other things. You could surround it with the H's, surround it with the oxygen. All right? Now, if you look at this, we have 2, 4, 6. We have 6 electrons placed, right? We need to place 6 more. Well, we know oxygen likes to have a couple of unshared pairs, so we could put a couple of pairs on there, right? We're still missing a pair of electrons. We've only mapped out 10. And also, you'll notice both oxygen and carbon have incomplete octets, right? So what can we do to fix that? Well, if we draw a double bond right there, that gives us a total of 12 electrons, and it also fills up the outer shell of both oxygen and carbon. So voila, this would be the Lewis structure for this formula. By the way, just a free bit of information, this is formaldehyde, which is a molecule that I'm pretty sure you've probably heard of before. We'll revisit formaldehyde certainly later on in the year. We'll be using it when we embalm our dead bodies. Just kidding. Perhaps. All right, let's try another one. Let's try a bigger one. That's pretty long, right? That's longer than the ones we've done. You approach it the exact same way, though, right? We're going to find out the number of valence electrons. We have 2 carbons, so we have 8 electrons. We have 1, 2, 3, 4 H's. Each one there we go. Each one contributing 1, so that's going to be 4 electrons total from H. And we have 3 oxygens. Each oxygen is going to contribute 6 valence electrons, so that's going to be 18. So overall, we've got 30. All right? And again, as you're mapping these out, you can kind of get a feel as you do it for, just sort of looking at it and seeing, sort of being able to tell how many bonds it's probably going to make. All right? So if I did something like this, if I said I had, if I'm looking at this, looks like I probably have an OH group, and this OH is probably going to be bonded to a carbon that has 2 H's on it. Then you have another carbon, and this carbon's going to have 2 oxygens. So we could put one here, and we could put one there. And finally we have 1 H. All right? So at this point, we've mapped out 2, 4, 6, 8, 10, 12, 14, 16 of our electrons, right? Well, we know that oxygen usually likes to have 2 unshared pairs, so we can place those. Okay. So we're kind of in a situation that we were with the last example now. We've got everything mapped out, but we see over here, this carbon's only got 6 electrons, this oxygen's only got 6 electrons. Again, we can draw a double bond and make it happy. So now we have 30 electrons mapped out. All the carbons, oxygens, and hydrogens are following their preferred bonding patterns. All right? Cool, cool. You know, I'm so in habit of doing this, over the years. I just automatically want to say, any questions? Does that make sense? And haha, nobody's going to talk to me but the voices in my head. So, if I do that, just overlook it. All right. Now, hopefully you guys are getting the hang of this for doing, neutral compounds. Like I said, we are going to run into charged species sometimes, all right? And this is going to introduce the concept of formal charge, all right? Let me show you how this works. Let's do an example. I'm going to pick something that you guys have seen before. This is the good old hydronium ion, H3O+, all right? Overall, H3O has a total positive charge of 1 over the course of the molecule. All right, we want to figure out exactly what the Lewis structure is and where that positive charge actually is located. All right, so you'd start this off like any other Lewis structure, right? You have 3 hydrogens, giving a total contribution of 3 valence electrons. You have 1 oxygen, giving you 6 valence electrons. Now, you're kind of looking at this and you're saying, oh my gosh, that's going to give us an odd number. How do we handle that? Well, if you see an odd number, at least at this point, that's going to be pretty good indication that you've done something wrong. In this case, we've forgotten to do something, right? Don't forget that earlier on I told you, if we have a positive charge, that means we have to subtract 1 electron from our total, right? So it's going to be 3 plus 6, but then we're going to subtract 1 from it. So that's going to give us a total of 8 valence electrons. At this point, whenever you calculate the total number of valence electrons to place, it should always end up being an even number. All right, so let's take a look at how to go about this. All right, now, you guys probably remember from Gen Chem that H3O, hydronium, is basically just a water that has accepted another proton. Right? So this is the structure of water, right? This is going to be the structure of hydronium. Oxygen has accepted an H, so it's got 3 H's and 1 oxygen. Normally, oxygen would have 2 unshared pairs of electrons, but guess what? It's already got 3 bonds, 6 electrons. It can't fit 2 more unshared pairs. There's just not enough room in the outer shell. So it's only going to have 1 unshared pair. Okay? Come on, there we go. And you'll see that we've mapped out 2, 4, 6, 8 electrons, which is good. However, we have not accounted for the charge. There's a positively charged area somewhere in this. We got to find out where it is. All right. There's a couple of different ways you can do this. All right. Number 1, this is my preferred way. It may not be yours, but I think if you can do it this way, this will help you out. What I like to do is I like to look at the electron density of each one of these, right? Each one of these has a full outer shell, but it doesn't necessarily mean they have the same electron density or full hold on electrons that they did before, all right? And I'm going to zero in on this oxygen, all right? If you look in a normal state, at neutrality, oxygen has 2 bonds and 2 unshared pairs. So that means normally when it's neutral, it's got 2 unshared pairs all to itself. It's being greedy. It's not wanting to share them with anybody, right? But in this case, right here, I'm just going to sort of make a scribble so you know where I'm pointing. On this oxygen and hydronium, it's still got 8 electrons, but it doesn't have quite a tight hold on them, right? Instead of having 2 pairs of electrons all to itself, it's kind of having to share it a little bit. It doesn't get to have those electrons all to itself all the time. So we would say this oxygen is losing electron density. It's still got 8 electrons in the outer shell, but it doesn't have as tight a hold. And when you lose electron density, you get more positive. So that means that oxygen is going to be positive. All right? And that is the center of positive charge. All right? That's one way to go about this. Now, if you don't want to, if you're having trouble with that, you can also do a mathematical calculation. You can actually calculate formal charge. Formal charge is going to equal the number of valence electrons of an atom minus the number of electrons owned by that atom. All right? Here's what we mean by owned. All right? If an atom has an unshared pair of electrons, those 2 electrons are owned. All right? Also, an atom owns 1/2 of all shared electrons. Okay? So if we look at this one, oxygen has 6 valence electrons. We're going to subtract the number of electrons owned. It's got 1 unshared pair all to itself, so that's going to be 2. And oxygen is also making 3 bonds. It can claim ownership of 1/2 of each one of those bonds, so it can claim ownership of 1 electron from each bond. So that's going to be 3. All right? So then you say 6 minus 2 plus 3. That's going to equal 1. Positive 1. And therefore you can do the mathematical calculation of any given atom and figure out what its formal charge is. All right. Let's try another one. Let's try this one. CH3, NH3, plus. Okay? All right, so we know we have a plus charge. It's somewhere on this molecule, but we don't know exactly where it is. All right, well, let's do the same thing we did before. All right? Carbon, we got 1 of them. We got 4 electrons. Nitrogen, we got 1 of them. We got 5 electrons. We have 6 hydrogens, so we're going to get 6 electrons from hydrogen. And since it's got a positive charge, we're going to subtract 1 from the total. So that is going to give us 14 electrons. All right. Well, let's see. If we map these out, a good place to start is put carbon in the center, as always. All right. So if we did that, that would give us 3 of our hydrogens and our nitrogen placed. We still need to place 3 other hydrogens, right? And as it turns out, we have room to do that on nitrogen. So again, every atom here in this structure is following the octet rule. We have 14 electrons mapped out. Can't talk right now. Now we got to figure out where that positive charge goes. So again, we could go through 2 processes. We could go through and calculate the formal charge of every one of these. I'm going to allude to the electron density. If you'll notice here, this nitrogen has 4 bonds and no unshared pairs, whereas usually at neutrality it likes to make 3 bonds and have 1 unshared pair. So this nitrogen is losing electron density, and it's going to have a positive charge. Otherwise, you could go through and calculate this. Nitrogen has 5 valence electrons. In this case, it's got ownership of 4 electrons, so 5 minus 4 is positive 1. Okay. All right, I want to do one more example. Okay. Let's try this. C3, nope, not C3. CH3, whoops, come on, CH3O. We're going to give it a negative charge. All right. Carbon gives us 4. H, since there's 3 of them, gives us 3. Oxygen gives us 6. In this case, we got a negative charge. So if you have a negative charge, you need to add 1 to your electron total, and that is going to give us 14 electrons. All right. Again, a good place to start is to make carbon a central atom. So we could put 3 hydrogens on it and then add an oxygen. All right. We're still missing 6 electrons here, but we do have plenty of room in oxygen's outer shell. So if we do that, we see that everything follows the octet rule. Carbon and oxygen have 8 electrons, hydrogen has 2. All right. Again, in this case, looking at the electron density, oxygen usually likes to share 2 of the electron pairs, but in this case, it's only having to share 1. Right? So instead of having 2 pairs of electrons all to itself, it's got 3. So that means its electron density is higher than usual, so that means oxygen's got a negative charge. All right. Again, you could go through and calculate this on your own for formal charges, through the formal charge calculation, or you could look at it through electron density. All right. Last thing in this video I want to do is I want to give you another chart that would be good to definitely learn and kind of make your life easier. All right, and that's specifying on the atoms carbon, nitrogen, and oxygen. So we looked at in the previous chart, what they prefer at neutrality. I'm going to go into that a little bit deeper now with these guys. All right. All right, so I want to look at different charges, just so you don't confuse this 0 for an O, letter O. I'm just going to put a slash mark in it. So we're going to look and see what carbon does at charges of 0, +1, and -1. Whoops, not negative N. That's weird. And then we're going to do the same thing for oxygen and oxygen and nitrogen. All right, so when carbon is neutral, it likes to have 4 bonds. So we'll just sort of draw them like that. All right. Carbon, when it's negative, is going to get to have one of those electron pairs all to itself, a higher electron density. So it's going to have a negative charge. When carbon is positive, you're going to see the only, dang it. Okay, sorry about that. When carbon is positive, though, you're going to see one of the few examples where we are allowed to have an incomplete octet. Carbon is allowed to do that because carbon is not an electronegative atom, right? If something's really electronegative, it cannot stand having an incomplete octet. Carbon, it can handle it. So if carbon is missing a pair of electrons like that, then it would attain a +1 charge. All right. Nitrogen, we said, likes to have 3 bonds in one unshared pair. All right. Nitrogen will attain a positive charge whenever it has to share that unshared pair that it usually likes to keep all to itself and loses electron density. Conversely, there are cases where nitrogen might get to have 2 unshared pairs and only make 2 bonds. That way it gets more electron density than usual and has a negative charge. All right. Oxygen is neutral when it has 2 unshared pairs and 2 bonds. And I think we've shown an example or two here where oxygen has different arrangements. Oxygen can sometimes share one of those pairs of electrons, lose electron density and give you positive. And there are cases where oxygen might actually have an extra pair of unshared electrons, increasing its electron density, giving it a negative charge. All right, so if you learn this chart and also learn the previous one I put on there, that will be, I think, a big help to you in drawing Lewis structures now and in the future. All right, so that's going to be the end of this particular video. Others are coming. If you have any questions along the way, feel free to let me know. Be sure to get lots of practice on this, and that will really set you on your way. Until next time, I will see you later.